Discrete Markov processes. Consider a system that at any time is in one of the set of n distinct states, S1, S2, S3 until Sn. The state at time t is denoted as Qt. T is the index starting from 1 to 3 and so on. So for example, Qt equals to Si means that at time t, the system is in state Si. So we write time as if this should be a temporal sequence. The methodology is valid for any sequences, be it in time, space, position on the DNA stream, and so forth. A regularly spaced discrete time system moves to a state with a given probability depending on the values of the previous states. That is the probability of Qt plus 1 conditioning equals to Sj, conditioning on the case that Qt equals to Si and Qt minus 1 equals to Sk and so on. Such kind of conditioning probability. And for the special case of a first order Markov model, the state at time t plus 1 depends only on state at time t, regardless of the states in the previous times. Yeah, that's what the Markov property called. So it can be represented as the following. That is the probability of Qt plus 1 equals to Sj conditioning on Qt equals to Si, Qt minus 1 equals to Sk, and so on. Such results will equals to a simple probability. The probability of Qt plus 1 equals to Sj conditioning on Qt equals to Si. And this corresponds to saying that given the present state, the future is independent of the past. This is just a mathematical version of the saying, today is the first day of the rest of your life. And we further simplify the model that is regularized by assuming that these transition probabilities are independent of time. That is, Aij is defined as the probability of Qt plus 1 equals to Sj conditioning on Qt equals to Si, and satisfying Aij greater than equals to 0, and the sigma of Aij summing for all j starting from 1 to n equals to 1. So going from Si to Sj has the same probability no matter when it happens or where it happens in the observation sequence. A equals to Aij braces is a n by n matrix whose rows sum to 1. This can be seen as a stochastic automaton, see figure 15.1. From each state Si, the system moves to state Sj with probability Aij, and this probability is the same for any t. The only special case is the first state. We define initial probabilities pi I, which is the probability that the first state in the sequence is Si. Pi I is defined as the probability of Q1 equals to Si. Satisfying the sigma of pi I summing for I starting from 1 to n equals to 1, and the big pi, which is braces of pi I, is a vector of n elements that sum to 1. In an observable Markov model, the states are observable. At any time t, we know Qt, and as the system moves from one state to another, we get an observation sequence that is a sequence of states. The output of the process is the set of states at each instant of time where each state corresponds to a physical observable event. We have an observation sequence O that is the state sequence O equals to Q equals to the set Q1, Q2, Q3 until Qt, whose probability is given as the probability of O equals to Q, conditioning on A and also big pi, is equals to the probability of Q1 times pi of, where pi ranging from the index t starting from 2 to big T, of the following term. P of Qt conditioning on Qt minus 1. So we multiply all the probability of Qt conditioning on its previous state in the time sequence, which is equals to little pi Q1 times A Q1 Q2 times A Q2 Q3 times A Q3 Q4 and so on until times A Q t minus 1 qt. And the pi q1 is the probability that the first state is q1. A q1 q2 is the probability of going from q1 to q2, and so on. We multiply these probabilities to get the probability of the whole sequence. And let us now see an example. This is from Rabiner and John in 1986 to help us demonstrate. Assume we have n arms where each arm contains balls of only one color. So there is an arm of red balls, another of blue balls, and so forth. Somebody draws balls from urns one by one and shows us their color. Let Qt denote the color of the ball drawn at time t. Let us say we have three states. That is, S1 equals to red, S2 equals to blue, S3 equals to green, with initial probabilities. That is, big pi equals to the transpose of 0.5, 0.2, 0.3, and Aij is the probability of drawing from urn J a ball of color J after drawing a ball of color I from urn I. The transition matrix is, for example, A equals to, it's a 3 by 3 matrix. 0.4, 0.3, 0.3, 0.2, 0.6, 0.2, 0.1, 0.1, 0.8. And given big pi, the transpose of the vector 0.5, 0.2, 0.3, and the previous matrix A, 3 by 3, it is easy to generate k random sequences, each of length t. Let us see how we can calculate the probability of a sequence. Assume that the first four balls are red, red, green, green. This corresponds to the observation sequence O equals to S1, S1, S3, S3. Its probability is P of O conditional A and big pi is equals to P of S1 times P of S1 conditional S1 times P of S3 conditional S1 times P of S3 conditional S3, which is pi 1 times A11 times A13 times A33, which is equals to 0.5 times 0.4 times 0.3 times 0.8, and that is 0.048. Now let us see how we can learn the parameters big pi and the matrix A. Given k, the transition matrix A, given k sequences of length t, where q t to the k is the state at time t of sequence k, the initial probability estimate is the number of sequences starting with S I divided by the number of sequences. That is, pi I hat is equals to the number of the sequences starting with Si, then divided by the number of sequences. That is, sigma of the one function of Qi to the k equals to S1 summing for all k, then divided by k, where 1 of b, that one function with b parameter b is 1 if b is true and 0 otherwise. So this is sort of like indicator. So as for the transition probabilities, the estimate for Aij is the number of transitions from Si to Sj divided by the total number of transitions from Si over all sequences. That is, Aij to the hat is equal to the number of transitions from Si to Sj divided by the number of transitions from Si. That is, the doubling summation, summing for all k and all t starting from 1 to capital T minus 1 of the term qi to the t equals to Si, qt to the k equals to Si, and qt to the 1, qt plus 1 to the k is equals to Sj. So this is the one function of qt to the k equals to Si, and the qt plus 1 to the k equals to Sj. Then divided by another one function enclosed within doubling summation, summing for all index k and summing for all t starting from 1 to capital T minus 1 of the results of the output of the one function for testing whether qt to the k is equals to S1 or not. Now A1 to hat is the number of times a blue ball follows a red ball divided by the total number of red ball draws over all sequences.